Hello everyone, welcome to this lecture. We are going to start talking about linear operators and eigenvalues. So eigenvalues, many people will argue, is one of the foundations, or not foundation, one of the most crucial and most applied part of linear algebra. So many linear systems, so many things in linear systems and engineering systems use eigenvalues as a core property. So you have to get a very good understanding of what they mean, what are eigenvalues, what are eigenvectors. A very conceptual and solid understanding is very important. Okay, so let's get started. Okay, so before we define eigenvalues, we have to define these things called linear operators. Okay, so it turns out linear transformations can go from R2 to R. Okay, so we've been so far thinking of linear transformation only from R2 to R2, but I can think of a linear transformation which goes from R2 to R. How would that look? Okay, any vector through this linear transformation T is going to go to a point in R, okay, and linearity should be maintained. Okay, how do you think of the matrix now? The matrix, the basis, there are two basis vectors here. So matrix with respect to canonical basis. The T, when it works on the standard basis vectors 1, 0, maybe gives you a real number A1. T of 0, 1 maybe gives you A2. So what is the matrix? The first column is just A1, second column is just A2. See, previously we were thinking of the transformation going to R2, so the first column had two values, but now the transformation is going only to R. So the first column has only one value A1, second column has only one value A2. Is that okay? So it's a little bit of a generalization of a transformation from R2 to R instead of saying R2 to R2. Okay. So what happens for a V which is xy, an arbitrary point in canonical basis? T of V will be this matrix A1, A2, which is a 1 cross 2 matrix. Okay, previously we were thinking of 2 cross 2 matrices because it went from R2 to R2. Now I am going from R2 to R, so it becomes a 1 cross 2 matrix. A vector of length 2 is input, but output comes a vector of length 1. Okay, so A1, A2, 1 by 2 matrix multiplying a 2 by 1 matrix will give you A1x plus A2y. Okay, I hope that's clear. Okay, so this is a transformation from R2 to R. You can also have a linear transformation from R to R2. Okay, you start from a point in R on the real line and you can go to R2. Again, the condition, linearity condition is satisfied. So if you have a canonical basis for R is just 1, right? Scalar 1, put in a vector like a coordinate. So this 1 maybe it goes to A1, A2. Now my matrix is just a 2 cross 1 matrix with A1, A2 as the first column. There's only one basis. So for that basis, the transformation gives you A1, A2. So you get a 2 cross 1 matrix. Okay. So what happens for an arbitrary vector V equals x in the real line? It multiplies the 2 cross 1 matrix to give you A1x, A2y. Is that okay? So I hope that's clear. So a 2 cross 1 matrix represents a transformation from R to R2. A 1 cross 2 matrix represents a transformation from R2 to R. Okay. So these are transformations which change dimension. Now, what is an operator? When you say operator, an operator will go from same dimension to same dimension, R2 to R2. Okay, you have R2, linear operator goes to R2. So this is what we've been studying all along. Instead of just saying transformation, you can say operator. Operator goes from the space of same dimension, same space to itself. Okay, R2 to R2, not just dimension being same, when R2 to R2. An operator does not leave the space. Okay, it takes vectors in one space back to another vector in the same space, R2 to R2. Now in the canonical basis, T of 1, 0 is A1, 1, A2, 1, T of 0, 1 is A1 to A2, 2, and the matrix becomes our familiar 2 by 2 matrix. The first column is this guy, second column is this guy. Okay, compare with the R to R2 and R2 to R and see how we use the same principles for finding the matrix, but except that the number of basis elements is different and the length of the output is different. Okay, that's all. So V equals xy in canonical basis, we know this is what happens in the operator. So from now on we'll study operators. It turns out these operators are very interesting. So we'll study operators much more closely when we look at eigenvalues, eigenvectors and all that. Okay, operators, input and output spaces are the same. Okay, thank you.